Hello everybody. So on this video I will explain the sensitivity analysis in linear programming. So in order to explain the concept of sensitivity analysis in linear programming, I will use the example that I am showing you right now on the screen. So in order to explain the concept of sensitivity analysis, I will use those 1, 2, 3, 4 equation. Now let's go. Before we solve the example, so the sensitivity analysis means we want to see the effect of the change in the model to our current optimal solution. So the change in the model can be the change in the constraint, that can be the change in the objective function. And we want to see the effect of those changes to our current optimal solution. And that is the sensitivity analysis. Now, the example here, we have an LP, and that LP is a maximization problem with all constraints are less than or equal to, and x4, x5, and x6 are these flex variables. Now problem A, find the value of beta. See here, we don't know the value of the z star, but on the problem we label the value of z star as minus beta, so we need to find the value of beta. In order to find the value of beta, we need to use equation number 1 and equation number 2. CB is the coefficient of the basic variables in the objective function, B is the basic matrix, and W is the dual optimal solution. Z, that is the value of the objective function, so minus Z is minus beta, and B bar, that is the value of the right hand side vector. So in this example, B bar is 2, 1, and 1. Now let's answer problem A. Now we know W is the location of W in the simplex table. It is right below the slack variables. So W is minus 1, 0, and 1. Okay, and after that we need to identify the B, the matrix B, or the basic matrix, and we know that right below the W, it is the matrix of B inverse. So this is the B inverse matrix. So the location of the B inverse matrix, it is right below the W matrix, but it is on the constraints rows. Okay, so our B inverse that is equal to 0, minus 1, and minus 2, 1, and 0, minus 3, 0, and 2. That's the B inverse. Okay, and what is B? B is the inverse of B inverse. So B is the inverse of B inverse. Okay, so we need to take the inverse of the B inverse matrix in order to get B. So the inverse of a 3 by 3 matrix is a 3 by 3 matrix. So since I'm using Excel, so I can use Excel to find the inverse of B inverse. But if we are not using Excel, then you need to do it manually. So the Excel formula to calculate the inverse of a matrix is M inverse. So we need to select the matrix that we need to find its inverse, and after that you need to press Control Shift and OK. So this is your matrix B. Okay, but we need the B transpose over here, so we need to find the transpose of B. So in order to do that, I need to copy value, and I need to copy and paste value the B matrix, and then I will do paste transpose. So this is the B transpose. Okay, now we have B transpose and W transpose, so we can have CB transpose. Now the CB transpose is B transpose times W transpose. So here our W, so our W transpose should be this one. This is our W transpose. Okay, now so we need to multiply B transpose and W transpose. A 3 by 3 matrix times a 3 by 1 matrix, and it is a 3 by 1 matrix. So in Excel, when you do matrix multiplication, then you use this equation, or this formula, M mu. So B transpose times W transpose. Control Shift. Okay. So oh, sorry, I think I made a mistake. This is our B, and this is the B transpose. There is no change, so I think I have the wrong B transpose. Then I will do it again. Okay, now this is the B transpose, and this is the value of your CB transpose. And then we will find the value of Z by using the second equation. So we have CB transpose, then we can have CB, and we know B bar. Those are the B bar. Okay, so since it is a max problem, so we will have minus Z. Okay, so minus Z equals to minus beta. So now we find Z. Z is CB. This is CB transpose. So CB is minus 5, 0, and minus 2. That's your CB. And the B bar is the right hand side value. And this is your B bar. Okay, so what is the Z? Z is CB times B bar. So a a 1 by 3 matrix times a 3 by 1 matrix, it is just a number. So we do the matrix multiplication. So this matrix times this matrix. Control Shift and Enter. So the value of z is minus 13. So since it is a max problem, so minus z equal minus beta. Okay. So what is that beta? This is the beta. Okay. So since minus z equal minus beta, so z so we know that minus beta equals minus 13. So beta, so we have beta, equal 13. So beta is, so or beta, it is just minus of the value of z. Okay. Oh, I'm sorry. So minus of minus 13. So beta is 13. Oh, I'm sorry. I think I made a mistake over here. So z should be minus beta. Okay. Z should be minus beta. Then beta is minus z because it is a max problem. So now we have the value of beta. So the value of beta is 13. So that's the answer for problem A. Now, oh sorry. Now let's do problem B. Suppose that we add x1 plus 2x2 plus x3 less than or equal 10 to the problem. So we are adding a new constraint. Is the current optimal solution still optimal? So in order to do that, it is very easy to solve. Okay. So B. So we know the value of x1. It is 2. So that's equal 2 plus 2 times x2. x2 is non-basis, so its value is 0. And then plus x3, and the value x3 is 1. So it is equal 3. So is 3 less than or equal 10? Yes, 3 is less than or equal 10. And therefore, because our current optimal solution satisfies the constraint, so our current optimal solution still optimal. So that's the answer for B. So it is still optimal. But when our current optimal solution does not satisfy the constraint, so our current optimal solution is not optimal anymore. Now let's do problem C. How large B1 or the right hand side of the first constraint can be met without violating feasibility? So we will use equation number 3. I think I have explained the equation number 3 from the previous video regarding the economic interpretation of the dual variables. So we know our B bar, this is the B bar, and we know the B inverse. So the xB prime is the new value of the basis variable. So xB prime, that's equal B bar, this is the B bar, plus B inverse. We know the B inverse. This is the B inverse. Okay, times T. So T is how much the right hand side that we will change. So we have three constraints. See, we have three constraints. So we will say that the change will be T1, T2, and T3. Since the problem only asks for the change in the B1 or the right hand side of the first constant, so T2 is 0 and T3 is 0. And when you do the operation over here, you will get 2 plus 2T1, and then 1 minus 2T1, and then 1 minus 3T1. And all elements of the matrix, remember, all x must be positive or 0. So they are all must be bigger than or equal to 0. Okay. Now from the first statement, 2 plus 2T1 bigger than or equal to 0. This means T1 must be bigger than or equal to minus 1. Oh, sorry. This is small T1. And from the second constraint, so that means 1 minus 2T1 must be bigger than or equal to 0. So that means T1 must be less than or equal a half. And from the third constraint, from the third inequality, we will get T1 less than or less than or equal to 1 over 3. Okay. Now, so it is very easy. 2 plus 2T1 bigger than or equal to 0. So that means T1 bigger than or equal to minus 1. So 1 minus 2T1 bigger than or equal to 0. So that means T1 less than or equal to a half. So from those three constraints, it means that so T1 bigger than or equal to minus 1. That means you can increase the value of T1 as much as you want, but the lowest value of T1 must be minus 1. From the second statement, we know that T1 must be less than or equal to a half. But the third constraint say that T1 must be less than or equal to 1 over 3. So from statement number 1, number 2, and number 3, we can conclude that T1 cannot be more than 1 over 3. Because when we say that T1 must be less than or equal a half, so the statement number 3 we will violate it. Okay, so in conclusion, so B1 can be decreased at most minus 1 unit, or at most 1 unit. Okay, and then B1 can be increased up to 1 over 3 unit, because when you increase it a half unit, so you will violate the statement number 3. So that is the answer for problem C. Now let's solve problem D. Problem D. So will the solution be altered if a new activity x7 with the coefficient a7111? So that's mean the coefficient of x7 in the constant is 1, 1, and 1. So the coefficient of x7 in the first constant is 1, in the second constant is 1, and the third constant is 1. And the coefficient of x7 in the objective function equation is also 1. So C7 equal 1. So in order to solve this problem, we will use the last equation. So we need to find the value of Z7 minus C7. Okay. We know W and we know A7. So we need to find WA7. So this is the A7. What is the W? Here is our W. So it will be just a number, because that is a 1 by 3 matrix times a 3 by 1 matrix. So that will be just a number. So that's equal W times A7, Ctrl Shift Enter. So that's it. So the value is minus 2, and then we minus WA7 with C7. So C7 that is 1, but since it is a max problem, so we need to times 1 with minus 1. So minus 1, that is minus 1. So the Z7 minus C7, that will be equal WA7 minus 2 minus the minus of C7, and that is minus 1. So that will be minus 1. So here minus 1 is less than 0. And remember, when all the value over here is less than or equal 0, so the solution is optimal. So since Z7 minus C7 is less than or equal to 0, then the conclusion is that our current the conclusion is that the current solution will not be altered or changed. So I think this is it for the sensitivity analysis, and thank you very much.